On April 20th, 2026, at 16 minutes before 5 in the afternoon local time, the seafloor beneath the northwestern Pacific Ocean moved. The Pacific Plate, which had been pressing westward and downward beneath the Okhotsk microplate at a convergence rate of nearly 9 centimeters per year, suddenly released a locked section of its interface approximately 100 kilometers east-northeast of Miyako in Iwate Prefecture, Japan. The rupture expanded through the plate boundary over a period of roughly 30 seconds. The moment magnitude assigned by Japan's meteorological agency was 7.7. The depth was 19 kilometers below the seafloor. This was not a minor adjustment. This was the plate boundary speaking. The first thing people on shore noticed was the shaking. Buildings in Aomori Prefecture rattled at upper 5 intensity on the Japanese scale. The same intensity was recorded in Iwate. The shaking reached Tokyo, hundreds of kilometers to the south, where high-rise buildings swayed with the long-period ground motion characteristic of deep-source surface waves crossing the broad sedimentary basin of the Kanto Plain. People reached for doorframes. Office chairs rolled across floors, water sloshed in glasses, and then the Japan Meteorological Agency did something it very rarely does. It issued a tsunami warning. Not a tsunami watch, not an advisory. A warning for waves potentially reaching 3 meters along the coastlines of Hokkaido, Aomori, Iwate, Miyagi, and Fukushima. Evacuation orders went out to 82,811 households, covering 175,957 people across 13 cities, 21 towns, and 6 villages. The sirens that lined the Sanriku coast, the same sirens installed after the catastrophe of 2011, began to sound. Japan executed the evacuation with the precision of a society that has rehearsed this exact scenario many times, because it has. Japan evacuates tsunami zones the way other countries practice fire drills. It is not theoretical, it is not precautionary, it is institutional memory written into law, infrastructure, and reflex. The waves arrived. At Kuji, in Iwate Prefecture, the tsunami reached 80 centimeters. At Miyako, 40 centimeters. At Urakawa, in Hokkaido, 40 centimeters. At Sendai, 30 centimeters. The warning was downgraded to an advisory, then lifted. 10 people were injured from falls during evacuation, from objects displaced by the shaking. 39 buildings were damaged in Aomori Prefecture. No one was killed. The immediate disaster was, by any measure, manageable. And yet the Japan Meteorological Agency then did something it has done only a handful of times in its history. It issued a large-scale earthquake caution, a formal notice to 182 coastal municipalities stretching from Hokkaido south to Chiba Prefecture, stating that in the week following the April 20th event, the probability of a magnitude 8 or greater earthquake along the Japan Trench and Kuril Trench had risen to 1%. 1% sounds small. In any normal week, that probability sits at 0.1%. The April 20th earthquake had made a megaquake 10 times more likely than baseline. That number 1 in 100 over 7 days represents a scientific community communicating something very precise to the public. This is not over. To understand why, you have to understand the machine. The Japan Trench is one of the most dangerous pieces of geography on the surface of this planet. It runs roughly north-south for approximately 800 kilometers along the eastern coast of Honshu and Hokkaido, from the Boso Peninsula in the south to the juncture with the Kuril Trench in the north. Here, the Pacific Plate dives beneath the North American and Okhotsk microplates at a convergence rate of between 7.9 and 9.2 centimeters per year. That may sound slow. In human terms, it is the speed at which your fingernail grows. In geological terms, it is extremely fast. Over the course of a single century, that motion accumulates 7 to 9 meters of potential slip along the locked portions of the plate interface. When that slip releases all at once, it moves the seafloor by meters in seconds, and the ocean above it moves with it. The Japan Trench dips at approximately 5 degrees for its first 80 kilometers landward of the trench axis, then steepens abruptly to about 15 degrees. The shallow dipping outer portion is where the largest earthquakes nucleate, because the relatively gentle angle allows large areas of the plate interface to remain in frictional contact locked for decades or centuries at a time. When they unlock, the energy release is proportional to the area. A rupture patch 30 kilometers by 30 kilometers might produce a magnitude 6 or 7. A rupture patch 300 kilometers by 200 kilometers produces a magnitude 9. The April 20th event ruptured a patch in the central to northern portion of the Japan Trench in the zone immediately north of the region most devastated in the 2011 Tohoku earthquake. This geographic detail is not incidental. It is the key to what this event means and to why the scientific community was watching so carefully in its aftermath. On March 11th, 2011, the largest earthquake in Japan's recorded history occurred approximately 70 kilometers east of the Yoshika Peninsula in Miyagi Prefecture. The magnitude 9.0 Tohoku earthquake ruptured approximately 500 kilometers of the plate interface, with slip displacement at the shallowest portion of the trench reaching in some areas over 50 meters. The rupture generated a tsunami that arrived at the Sanriku coast within 20 to 40 minutes. In some funnel-shaped bays and harbors, the waves exceeded 15 meters. In Miyako, they reached 11 meters. In areas with particularly favorable topographic geometry, run-up measurements exceeded 40 meters. The tsunami penetrated up to 10 kilometers inland across the flat coastal plain of Sendai, traveling at the speed of a jet aircraft in open ocean and carrying everything in its path: houses, cars, ships, people, as a debris-laden wall of water. 19,747 people died. Another 2,500 remain officially missing. 340,000 people were displaced. It was the most costly natural disaster in Japan's history and the fourth most powerful earthquake ever recorded on the global seismograph network. The world knows this story. What is less widely understood is what happened to the Japan Trench after 2011 and what it means for 2026. The 2011 rupture released an enormous amount of accumulated strain, but not all of it, and not uniformly. The rupture zone was centered on the Miyagi-Fukushima segment of the trench. The segment to the north from Iwate through Aomori into the southern Hokkaido coast had been partially loaded by the centuries of interseismic strain that preceded 2011, but did not rupture in the main shock. Post-2011, geodetic studies using GPS and satellite INSAR showed that the northern segments of the Japan Trench experienced significant changes in their stress state as a consequence of the 2011 event. In some areas, Coulomb stress transfer from the main shock brought northern segments closer to failure. In the 15 years between 2011 and the April 20th event of 2026, the Pacific Plate continued its subduction at 9 centimeters per year. That accumulated another 135 millimeters of potential slip on the still locked northern segment. The April 20th magnitude 7.7 event represents some fraction of that accumulated energy releasing. The scientific question that was open in the hours and days after the event was the same question the JMA's special advisory was communicating to the public. Was this a main shock, or was it a foreshock? That question cannot be answered in real time. It is only answerable in retrospect. The Japanese seismological community knows this, has been burned by it, and communicates it honestly. When the JMA says there is a 1% chance of a magnitude 8 or greater in the following week, they are saying, our models, our historical data, and our physical understanding of fault mechanics all tell us that this event may not be the largest earthquake associated with this episode of plate boundary strain release. They are also communicating something the broader public rarely hears from scientific agencies. We do not know what happens next. Here is what history says about the Sanriku coast and what it does not know. The 869 Jogan earthquake struck in the 9th year of the Jogan era, in the first year of a reign that would not survive the geological violence of the plate boundary to its east. The earthquake and the tsunami it generated devastated the Mutsu province on the eastern coast of Honshu. Ancient chronicles describe a roaring wave that inundated the Sendai coastal plain as far as the eye could see. Modern paleo-tsunami research, geological excavation of sand layers in coastal marshes and lake sediments, has found that the Jogan tsunami deposited a distinctive sand layer as far as 4 kilometers inland across the Sendai lowlands. The event has been reconstructed as likely a magnitude 8.4 or larger, with a rupture extent comparable in some studies to the 2011 event. The key fact is this: 869 and 2011 are the two largest events in the paleo-tsunami record for the Sendai coast. The recurrence interval between them is approximately 1140 years. The average recurrence interval estimated from the broader tsunami deposit record, including smaller and less complete events, is on the order of several centuries. The Japan Trench segment that ruptured in 2011 is, by most models, now in its post-seismic relaxation phase. It will not rupture again at that scale in any of our lifetimes. But the segments to its north and south are a different matter. The northern segment, the one adjacent to the April 20th rupture zone, last produced its own large earthquake in historical or instrumental records, with the 1933 Showa Sanriku earthquake, a magnitude 8.4 event that generated a tsunami killing approximately 3,000 people. That was 93 years ago. At 9 centimeters per year of subduction, the Pacific plate has moved approximately 8.4 meters closer to its next rupture since 1933. The question of how much of that accumulated strain was released by the April 20th event and how much remains stored on locked segments north and south of the rupture is one that seismologists are currently working to answer using the aftershock distribution, the moment tensor solutions, and the geodetic measurements being taken from GPS networks and from satellite-based INSAR. There is another layer to this story that the daily news coverage has not reached. In the months before April 2026, a research group at the Earthquake Research Institute of the University of Tokyo published a preprint examining the coupling state of the northern Japan Trench using a combination of ocean bottom pressure sensors, seafloor geodetic benchmarks, and 20 years of GPS data from onshore networks. The paper proposed that a segment, approximately 150 kilometers long in the zone between the northern end of the 2011 rupture and the southern terminus of the Hokkaido segment, showed anomalously high seismic coupling, meaning it was not creeping, not releasing strain incrementally, but accumulating it in the locked state, and had been doing so continuously since before 2011. The paper noted that this segment produced neither large co-seismic slip nor significant afterslip during and after the 2011 event, suggesting that it remained locked even as the plates around it moved. The estimated accumulated strain on this patch, if it were to release in a single event, corresponded to a moment magnitude of approximately 8.1 to 8.3. The paper was submitted in January 2026. It had not yet been peer-reviewed when the April 20th earthquake occurred in precisely the geographic zone the authors had identified as the most concerning locked patch on the northern Japan Trench. The April 20th event may have partially released that patch, or it may have brought the remaining locked section closer to failure. The distinction is everything. And in the days following the earthquake, as aftershocks continued to populate the seismograph records of dozens of monitoring stations, and as geodetic measurements from the GeoNet GPS network showed the co-seismic and post-seismic deformation patterns, the seismological community was doing what it always does: measuring, modeling, arguing, and arriving at a probability estimate that it would communicate honestly and imperfectly to the public. The seawalls are a part of this story too. After 2011, Japan undertook the largest coastal engineering project in its history. Along the Sanriku coast, it constructed a network of seawalls, some reaching 13 meters in height, several stretching for kilometers along coastlines that had been open to the sea for centuries. The total cost exceeded 12 trillion yen. The engineering was extraordinary. The ambition was to build a barrier between the Sanriku coast and the ocean that had killed its people in 1896, in 1933, and again in 2011. But there are honest debates within Japan's disaster science community about what the seawalls actually provide. They are designed for the L1 tsunami, the most probable tsunami, associated with magnitude 8 class earthquakes, occurring perhaps once every 100 to 150 years. They are not designed for the L2 tsunami, the maximum credible event associated with the rarest, largest earthquakes, the kind that occurs on 1,000-year recurrence intervals. The 2011 tsunami was an L2 event. A seawall designed for a 3-meter wave does not save a town from a 10-meter wave. What it may do, in the intermediate magnitude range, is provide the critical extra minutes that allow complete evacuation, the scenario that played out on April 20th, 2026, when 175,957 people moved to high ground and the waves arrived at 80 centimeters. But the deeper truth about the seawall debate is what it reveals about the nature of probabilistic risk. The communities of the Sanriku coast are not arguing about whether earthquakes will happen. They are arguing about how to live alongside a plate boundary that has been producing tsunamis for as long as there have been people on this coast, and that will continue to do so for as long as the Pacific plate is subducting beneath Japan, which is to say, indefinitely. The plate boundary does not negotiate. It does not recognize the seawalls, the evacuation drills, the detection buoys, or the warning sirens. It operates on its own timescale, accumulating strain through the decades of human lives, releasing it in the 30 seconds of a rupture, and then accumulating again. There is a forward question embedded in every aftershock of the April 20th event. The Nankai Trough, along Japan's Pacific coast to the southwest, is a different subduction zone, the Philippine Plate diving beneath the Eurasian Plate at a convergence rate of approximately 6 to 8 centimeters per year. It has its own history of great earthquakes and tsunamis, including paired M8+ events in 1944 and 1946. The Japanese government's Central Disaster Management Council has estimated that a full rupture of the Nankai Trough, a scenario involving simultaneous or near-simultaneous rupture of the Tokai, Tonankai, and Nankai segments, could generate a moment magnitude 8.7 to 9.1 event, produce tsunami waves reaching 34 meters in some areas, and cause up to 320,000 fatalities. The Japanese government has been preparing for this event for decades. The Nankai Trough has nothing directly to do with the April 20th Sanriku earthquake. The two subduction systems are geologically and geographically separate. And yet the April 20th event serves as a reminder that Japan is not one subduction zone, it is several. And while the seismological attention in the days after April 20th was focused on the northern Japan Trench, the Nankai system continues its interseismic loading to the south, its coupling ratio high, its accumulated strain increasing each year, and its timing unknown. There is one more number that needs to be said clearly. The 1,896 Meiji Sanriku earthquake struck on June 15th, at the end of a long day, during the celebration of a military festival. The magnitude was approximately 8.5, but the shaking at the coast was mild enough that most people did not evacuate. This event was what seismologists now call a tsunami earthquake, a slow rupturing event whose low frequency of seismic energy gives it a deceptively small shaking intensity at the shore, while the long fault displacement produces a tsunami disproportionately large for its felt intensity. The waves arrived at night. They reached 28 meters at Riori Bay. They killed 22,070 people in under 30 minutes. Those 22,000 people had no warning. They did not know that the ocean could behave this way, that an earthquake you could barely feel could send a wall of water 30 meters high through your village before the night was over. That knowledge now exists. It is encoded in the warning systems, the evacuation maps, the sea walls, the education programs that begin in elementary school. On April 20th, 2026, at 16 minutes before 5 in the afternoon, 175,957 people moved away from the coast because a system built from the memory of 22,070 deaths in 1896 told them to. They moved. The waves came. They were smaller than feared. Nobody died. This is what 22,000 deaths bought. It bought the knowledge. It bought the systems. It bought the seconds of warning that let 175,957 people live. And the plate boundary that killed them in 1896 is still there. The Pacific Plate is still moving. The northern Japan Trench is still accumulating strain. The seismologists are still measuring, modeling, and debating the coupling state of the lock segment they identified in January. The JMA advisory has expired. The extraordinary watch that was placed on the Sanriku coast in the week after April 20th is now lifted. People have returned to their homes. The boats are back in the harbours. The fish markets are open. The sea floor does not care. It is 9 centimeters closer to its next rupture than it was before April 20th. What that rupture will be, a 6, a 7, a 7.7, an 8.3, a 9, and when it will come next year, next decade, the next century are questions the planet is not prepared to answer on a schedule humans find convenient. What the science can say is this: the probability is not zero, the systems are not perfect, and the 22,000 who died on a June night in 1896 are the reason, the only reason, that 175,957 people are alive tonight.